So we are almost finished here. Let's remember what we have done. We have selected theta and phi with respect to this coordinate system, orthonormal bases, W, V, and U. So we created this orthonormal bases. How did we create this? We had the intersection point P. We transformed it to the local coordinate system of the sphere. So whatever transformation the sphere has, we have applied the inverse of it so that P comes to the local space. Okay, so C was the center of the sphere. So using P and C, we created W, and then after we computed W, so this is like this vector, right? After we computed W, we created U and V vectors, which are unique up to a rotation around W. And from there, we have sampled theta and phi. Remember that this angle was here, this was theta max, okay? And same here, this was theta max. So the theta and phi we sampled are going to be used to create a vector. Now let's imagine that we have a vector like this. Okay, so let's call this vector L. Okay, so this vector, I mean, what do we say traditionally? Like this is don't we write it like this is the theta, okay? So this is the theta, the angle it makes with the theta, and this is the phi, right? So here now we are going in the opposite direction. Sometimes we have L, and from L we compute theta and phi, but now we have theta and phi, and we will be computing L. Okay, and theta and phi are with respect to UVW system. Okay, so these are with respect to UVW. So we can then write L as follows. L is equal to cos theta. So let me write, first let's write W cos theta plus V sin theta cos phi. Okay, V sin theta cos phi plus U sin theta sin phi. Right? So we can write L using the cos theta and sin theta sin phi like this. Okay? You can also go in the reverse direction, right? So how much so how much L goes in the W along the W axis? L goes cos theta, right? L goes this much in the W axis, right? And this is cos theta. How much L goes along the V axis? L goes like this much along the V axis, and this is sin theta cos phi. And similarly, L goes this much in the U axis, and this is sin theta sin phi. Okay, so using theta and phi, we can compute our. Okay, sorry for the doorbell. So you. Okay, so using theta and phi, we can compute L. Now, one thing that we need to do as the last thing is, here we have been working in the local coordinate system of the sphere, right? So we must convert L from, so this is L local. We must transform this L local to, we must transform it to L world. And similarly, so this is, let's call this P local. We must transform P local to P world. Okay? Now we know how to do this. We know the transformation of the local to world transformation of the sphere, right? So we simply multiply with that transformation matrix L local and P local to obtain the world, this direction and this point in the world space. An important thing, please don't forget, L world or L is a vector. Okay, L is a vector. So when we apply the transformation, it should not get affected by the translation. So please pay attention to that. But P is a point. Okay. Well, you actually know what is P world to begin with, right? When when we were intersecting our original ray with the objects, we have found P world first. But to do this sampling, we transformed it. So actually, you don't need to compute P world again. We already know this. Okay. Now, once you have this point, once you have obtained this transformation, what we do as the last thing is we must intersect, we must create a ray. So let me clean this part. Okay, so we create a ray RT, which is equal to P world plus T times L world. Okay, can you see this? Maybe I can write it a little bit here. RT is equal to P world plus T times L world. Our classic ray equation. Okay, so we create this ray. What do we use this ray for? We will intersect this ray. Okay, so we will intersect this with the sphere. Okay, so actually in world space we make this intersection. Now when we make this intersection, we may actually find that in the world space there was an object here. In between here there is an object. So it is possible that the direction that we have generated, after so much work, actually doesn't really matter because there's an object in between the point and in between the point being shaded and between the point that we are sampling light from. Okay, it is possible, but we intersect this ray with the sphere to find what? To find the actual point on the sphere from which we will be sampling the light from. Okay, so we do not directly sample this. Okay, so maybe we are doing too much work for nothing, you can say. We could actually randomly sample a point on the sphere by assuming that by accepting that some of these points may be behind. Okay, by accepting that some of these points may be at the back of the sphere, and then you don't have to go through this work. But alternatively, if you go through this work, you find the ray equation and you intersect the ray with the sphere to find the point from which to get light. Now, the radiance is going to be this is maybe I think I may have forgotten to mention this in the mesh light sources, but they are going to be defined by their radiance. Okay, so the radiance that we get from this point is going to be L. It could be constant, or it depends, right? Maybe there's a texture associated with it, an HDR texture, for instance, and the radiance could be the value at that coordinate on the sphere. Okay, so let's say the radiance is L, and remember the probability of selecting this direction was, okay, so let's write this. The probability of selecting this direction was equal to 1 over 2 pi 1 minus cos theta max. Okay, so once we get the radiance, once we do this computation, right, in Monte Carlo we compute Lx Wi. Okay, so this is going to be the L that comes from this direction, multiplied with the BRDF x Wi Wo, multiplied with the cos theta I, and we divide it by the probability of sampling this direction. The probability of sampling this direction, PW, is equal to this one. Okay?